Hey everyone! In today's video, we're going to look at a 2D momentum elastic collision. It's a lot like 1D momentum, and hopefully you'll see the changes. So a 5 kilogram rock is sliding 3 meters per second at 280 degrees from the x-axis. It strikes a second rock that is 8 kilograms and sliding at 4 meters per second at 340 degrees from the x-axis. After the collision, the first rock bounces away. It bounces. That is our indication that this is an elastic collision. They are not stuck together. It bounces away at 3.5 meters per second at 60 degrees from the x-axis. What happens to the second rock? The difference between one-dimensional momentum and two-dimensional momentum, this is the big thing in this video, is that x and y momentum are dealt with separately. Okay, x and y momentum are dealt with separately. So we're going to do all of the x momentum, then all of the y momentum, and then we'll get our final answer. So let's get that velocity x component first from our momentum. We're going to set up a little bit of a modified momentum equation where we have only the x components of our velocities. So to do that, each velocity we're going to multiply by the cos of the theta. If you've watched enough of my vector videos, you should know by now, if you multiply any vector by the cos of its angle, it's going to give you the x component. Note that we don't have an angle for that final velocity x. We're just going to solve for that because we don't know the diagonal component. We're going to fill them in. We have mass 1, v1, and that cos 280, plus our mass 2, which was 8, its velocity, which was 4, and its angle, which is the cos of 340. That's going to equal, back to the mass of the first rock, times its new velocity, times the cos of its new angle, 60 degrees. That's going to equal, or plus 8vx. Okay, we've filled everything in. We have all of these values set up, and it looks like so much. But these are just nice numbers. We can put these in the calculator. We chug out that left-hand side. It just equals 32.675. We chug out the right. It's 8.75 plus 8vx. We can simplify this, bring the 8.75 to the other side by subtracting. 23.925 equals 8vx. Divide both sides by 8. Vx equals 3 meters per second. Our rock, we don't know how much it's going up or down, but it's going 3 meters per second to the right. Let's go ahead and do our y momentum and figure out the second half of this. Once again, we're going to set up a modified momentum equation, except this time, instead of coses, we're going to be using sines, because sines of thetas give us the up-down components. So we have m1 v1 sine theta 1 plus m2 v2 sine theta 2. See, it's the momentum equation. It just has sines in it. Equals m1 v1 prime sine theta 1 prime plus our mass 2 times our y component of our velocity. We're just going to plug these things in. No problem. You just have to read these off the question. The mass of the first rock, the velocity of the first rock. In fact, you'll notice that this is identical to the x calculation, except that we're using sines instead of coses. So if you can do this once, you can do this twice. You've got the x, we're just filling in the exact same ones as our sine theta prime, our mass of our second rock, vy. We hit up the calculator. Even if it looks like a mess, it's a nice number, well, nice enough. Negative 25.72 equals 15.16 plus 8vy. We subtract 15.16 from both sides. We get negative 40.88 equals 8vy. Divide both sides by 8, and we get negative 5.11 meters per second. This rock is going down. We have our Vx, 3 meters per second to the right. We have our Vy, negative 5.11 meters per second down. You know what's coming next. It's vector time. Let's draw ourselves a triangle. So we're going to move this up, and I like to put a little dot where I know I'm starting my triangle. We move to the right first. That's our 3 meters per second to the right. We move down next. That's our 5.11 meters per second. And that nice little hypotenuse, that's going to be our final answer. That theta, we're going to need that later to tell our direction. To get the hypotenuse, we do a little bit of Pythagorean Theorem. If you're watching this, Pythagorean Theorem should be nothing for you. A squared plus b squared. The c squared is 35.11. Take the square root. It's 5.9 meters per second. We know how fast the rock is moving. We just got to figure out which way is it going. Tan of theta, because we have the opposite and the adjacent, is equal to 5.11 divided by 3. We do the inverse tan of that ratio, and we get 59.6 degrees. But be careful! That is the reference angle, not our standard angle from the x-axis. In order to get the standard angle, in this case, it's 360 minus that theta value, which equals 300.4 degrees from the x-axis. We finally know what's happening to this second rock. The second rock is now going to be cruising away after this collision, and it's going to be going 5.9 meters per second. What direction? It's going 300.4 degrees from the x-axis. That's it, folks. It's a lot of extra calculations from one-dimensional momentum, but it is a lot of repetitive calculations. And if you can do vectors, I believe that you can do this. I hope that it was a help. Thanks a lot for watching, and looking forward to seeing you next time.